All right, who wants to share what they got, what their results were? I've seen a couple of you guys, and you're making some good progress. If I've got cosine over sine, I want to volunteer. Or I'll just choose someone. Yeah? Yeah? Peyton, you want to take this? Thank you. Awesome. Alright, so we're kind of seeing that same pattern, but instead of going a point and then a vertical asymptote, it's the opposite. We saw a vertical asymptote and then a point. So it's not quite the same as tangent, it's kind of opposite, right? Because it makes sense, because we flipped it. Okay, and then what do you think's going on inside? Any guesses there? So right here's positive. Great. Cool. All right, so it's going to be opposite. So I'm going to kind of draw this in a different color. So it was positive right here and switched to negative, which meant those snakes are now going which way, guys? Snakes slithering down. So that's one of the biggest differences between tangent and cotangent, is that on tangent they're slithering up, and on cotangent they're slithering down. How many of you guys kind of came up with that on your own? All right, well then I chose the right people to comment. Okay, let's go over and throw up Desmos now on your screens. And I'm going to close these ones out. And let's just graph tangent and see, does that look like what we thought it'd look like? We have our snakes slithering up. Awesome. And notice in tangent, 0 was one of our points. And we had the vertical asymptotes at pi halves and negative pi halves. Okay? Then, if I look at cotangent, or 1 over tangent, ooh, isn't that such a fun art project here you got going on? Snakes are slithering down, but notice they're not at the exact same points. They've been shifted over by pi halves. Okay, so now, warm up your hands. I got to clear these out. Show me with your hands what sine looks like. This is where you got to use your dancing skills, right? Do this whole thing. Okay, sine and cosine. What about cosecant and secant? What do they look like? Go from the U's and the flipped U's, doing that whole thing. What about tangent? What does tangent look like? We got the snake slithering up. What about cotangent? Snake slithering down. Okay, cool. That's what we're just going to transform those using the same things you've done before. That wasn't too bad, right? Especially since you guys know why they look like that. All right, so let's just do a couple of transformations. We'll call this good. So, you guys, we just did that on Desmos, so I'm going to skip that, okay? But let me just show you real quick. The trick to graphing, like a lot of these, is to graph sine over, or to graph sine or cosine. So let me show you how I would do this, and maybe that's going to help you, because you're going to need to graph these over and over, especially with your transformations. Start with your parent function. So if I were doing, let's do cosecant first. What is cosecant the reciprocal of? It's going to be the reciprocal of sine, right? So what I'm going to do here is I'm going to start by graphing sine. And we've graphed it a lot, so hopefully you're getting used to it. And we're going to do that. How does that graph of sine help us, guys? Peaks and valleys are going to be used. And then what about when sine is 0? What goes there? We put the vertical asymptotes when sine is 0, because that would be when we're dividing by 0. And then, at the peaks and valleys, we're just going to put in the u. I'll do that different color so we got it there. And hey, just like that, we got cosecant. That didn't take too long, right? As we get more practice, this goes faster and faster. Okay, so then, Tao, tell me how we're going to graph secant. What is secant the reciprocal of? Remember that the first letters don't match up. So with sine, the reciprocal is cosecant. So secant, the reciprocal is cosine. So I'm going to graph cosine real quick. Starts and stops. The period is 2 pi. So here are my points like that. And then our thought process is just going to be the same as last time. Anywhere that cosine is 0, we're going to see a vertical asymptote. And then at the peaks and valleys, we're going to see the u's and the flipped u's. And there is secant. Okay, now with tangent and cotangent, sometimes people are like, do I need to graph both of them? And my advice would be just to graph the denominator. Like, do I have to graph both sine and cosine? Sorry, let me clarify there. Because we're going to think of tangent as sine over cosine, right? Because it's opposite over adjacent or y over x. But I would say, hey, just graph the denominator, because what don't we want to have happen here? We never want to divide by 0, right? Well, when cosine is 0, that's a clear indicator of when we would be dividing by 0, which is where we would see our vertical asymptotes. So I'm going to start again by graphing cosine. Now, when cosine is 0, what's going to show up on our graph? The asymptotes. Good job. Now, where you got to be just a little bit careful on this one is remember that when cosine is 1 or negative 1, it's actually then going to be, we're going to do, that's in the denominator, it's going to be 0 over 1 or 0 over negative 1. So that's going to become 0. So anywhere that I see 1 or negative 1, I'm going to put a 0. Now, is tangent going up or going down? Up. So it snakes slithering up like that. All right, now let me pause you. Does that make sense how to graph tangent just based off of cosine? When we first did it, we did sine, cosine, and divided them. But now we're just doing the denominator. Are you okay with that? Okay, you're going to have to graph these kind of on your own, so I want to make sure you're good. Okay, so then what do you guys think our strategy is going to be with cotangent? Yeah, because this is cosine over sine, so we're just going to graph sine. So let's take a second and graph sine. Are you guys getting faster at graphing sine and cosine? Or am I just going too fast? Okay, so I graphed sine because I want to make sure this is never equal to 0. So anywhere that sine is equal to 0, we're going to have a vertical asymptote. And if you compare it to tangent, they're going to be opposite, where we have our zeros and where we have the asymptotes. And anywhere that sine is 1 or negative 1, those are going to become zeros, x-intercepts. Alright, but Brenda, which way are the snakes going for cotangent? There we go. They're yelling timber. Yes, they're Kesha snakes. Alright. Cool beans. Cool beans. Can we move on? We're almost done. I know there's still a few slides, but it's not too tricky. You're just going to take these and do basic transformations. I feel like on this one, I don't even want to do it. What are you going to do with your tangent? What does tangent look like? Snakes going up. What are you going to do with all of the snakes going up? You're going to move it up 2. Now, there's only one key point. It's going to be the x-intercepts, right? So let's just take a quick peek at tangent. What does tangent look like? Tangent has an x-intercept at 0, and then the vertical asymptote at pi halves, x-intercept at pi, right? So I'm going to just copy down the key points here. So we have an x-intercept here, but then it was a vertical asymptote at pi halves, right? And then an x-intercept here, vertical asymptote at 3 pi. And make sure you're careful with your spacing, that you don't make it too much or too little, okay? Does that match up with your parent function for tangent? Awesome. However, when we're going to do the plus 2, all that's going to do is move those x-intercepts, those zeros, to 2. That wasn't too bad, right? That was pretty easy. It just took the snakes slithering up and we shifted them up. Give you a couple seconds to finish that, and then let's look at 12, or page 12 here. Okay, this one's going to be just a little bit tricky, but let's think about it. So I'm going to ask Ofa to help me out here. Ofa, if I see that 2 on the inside, what is that affecting? Perfect. So here's what I want you to do, is I want you to think of this. What's the reciprocal of cosecant, guys? So I want you to think of this as, let's start by graphing the sine of 2 theta. Now, Ofa gave us great advice. She said the period is 2 pi over whatever that number is, which in this case is 2. So what is the period going to be? Just pi. So let's start by just graphing sine of 2 theta, which is going to be sine where the period is pi. So that means sine starts at 0, and now it's going to end at pi. That means halfway is pi halves. So here is pi fourths, 3 pi fourths is the minimum, pi fourths is the max. And then it's just going to repeat that. So we're able to fit in 2 sine waves in the time it normally takes us to only do 1. We're going through twice as fast. Alright, now that we've set this up, everything from here should be good. What are we going to put at the x-intercepts? Asymptotes. Okay, what are we going to put at the maximum points? U's, and at the minimum points? Flipped U's. Okay, now usually, how many U's do we see in one cycle between 0 and 2 pi? We should just see 2. We have 1 up and 1 down, right? Now we see twice as many because of that 2 on the inside. It changed the period, it changed the frequency. Okay? So what I would recommend is with those ones, go back to what sine and cosine look like and start by graphing your parent function, and then it makes that easier. Can you do that on your own? Cool. Ooh, okay, this one is going to be fun. Same idea here. What is the reciprocal of secant? Is what now? Now, in instead of thinking of plain old cosine, what should we think of? Let me back up here. Angelina, what does that 3 change? So what will secant look like if its amplitude is 3? Well, let's graph its inverse, or not inverse, sorry, its reciprocal. Let's graph 3 cosine of theta. So Angelina, what will 3 cosine of theta look like? There you go. So where does cosine start at? But now it's going to be at 3. Length of one cycle is 2 pi. So then halfway at pi, it's going to be down at negative 3. So that means I have an x-intercept at pi halves, 3 pi halves, etc. So what I'm going to graph here, this is 3 cosine of theta. Okay, so then is our thought process any different? We just put vertical asymptotes at the x-intercepts. And then what do we go from there? Use and flip use. Isn't that pretty? Like, no, it's awful. Okay, let me actually just show you what this would look like on Desmos, okay? So if I wanted to do 3 cosine of x, that's what it looks like. It's just got an amplitude of 3. But then let's do 3 secant of x. And let's see what it looks like. There we go. It just stretched out cosine and then added the u's on top. Doesn't that look fun? I think it looks great. Nice and symmetric. Pretty design. Okay. I want you to take 20 seconds, turn to your neighbor, and talk about what the transformation is and what that will do. What shape is it going to make, and what does that do? Go. Let's come back in 3, 2, 1. So, Kara, I want you to tell me first, what does cotangent look like? There are going to be our snakes. Which way are snakes going here? Snakes slithering down. Great. What does that minus pi halves do to those snakes slithering down? There you go. We're going to the right by pi halves, which if I look at my scale, the scale is pi 4, so how many units are we going to go? We're going pi halves, that's 1, 2 units, right? Okay. So I'm going to look back at my cotangent here. And cotangent, do we see the vertical asymptote first, or do we see the point first? Asymptote, so it goes asymptote, point, okay? So I'm going to just kind of put those in here to begin with. I'm not going to graph the whole thing. But what we saw was we saw an asymptote here, and then a point here. And then an asymptote at pi, and then a point at 3 pi halves, and then another asymptote there. Now, what did we say to do? We're going to go and move everything to the right 2. That will move the point, but what also does this move? The asymptotes also move. So wherever the asymptote was before, I'm going to put a point, and wherever the point was before, we're going to put an asymptote. So it's almost making it look like what tangent will look like, except we're still going to be slithering down. Because cotangent is snakes slithering down. So it's going to be like that. And there you go. Wasn't too bad, right? Okay, here's what I want you to do, is I want you to, these are our last ones, I want you to, first off, with both of them, figure out what shape do they make, then figure out what are the transformations, and then try to graph them, and how can you check your work. Desmos. Okay, let's give it a shot.